Say the test would be take home. I said part of the test would be take home.
Oh.
No,
That's
that's
so
so
false.
good.
Yeah, that's yeah, just better than
Let's go back to the recording.
fill out your.
Yeah, let's go back to the recording.
Poopy.
Asterisk plus C.
Oh, it's got a more positive outlook on life. You guys are half-empty type people. Okay, a couple quick things. We have done derivatives already, as you recall, and we talked about if you start with a position function and you take the derivative of the position function, you get velocity, and you take the derivative of velocity, you get acceleration. So now if we go backwards, if we take the integral of acceleration, we'll get velocity. If we take the integral of velocity, we'll get position function. We'll practice that more in the future. However, there are a couple of quick things that we can look at. And I guess before I proceed, I should ask you the question. Do you understand the difference between displacement and total distance?
Yeah.
Thank you very much. What is it? John?
Displacement is relative to a starting point, while total distance is just like absolute.
Okay, so if I start here, and I think this is a samba. So I samba up, and then I samba back. And then I samba up a little bit further because I'm having fun. And then I samba back a little. This is a samba, right? Anybody know?
Yeah.
Zero displacement
Good.
samba.
What's my total displacement, John? What's my total distance?
Quite a bit.
John? I'm sorry?
The sum.
Yeah, well,
Yeah.
whatever.
The entirety of
12, 14 feet, however far I just sambaed and am exhausted. So we can use calculus to work out these two different things, and they appear to be the exact same thing, except that there's a little absolute value symbol in there. So if I have a velocity function, I can take the integral of the velocity function, and that will give me the total displacement. And for the samba, I would end up with it being 0. However, if I slap an absolute value around that, I would get total distance. Are you going to be calculating these by hand? No, because we still don't know how to do an absolute value integral, but it will pop up on the calculator portion of the test. And we'll go through a couple problems like this later on when we start talking about something called rectilinear motion. Yes, sir?
How can that be like the absolute value? Like, how can this be like the same absolute value?
Because if I move forward, I get a positive answer.
Uh-huh.
If I move backwards, I get a negative answer, right?
Uh-huh.
So without the absolute value, I'm adding positive distance and negative distance over and over again. So I stepped up, I traveled 4 feet, I backed up, I did negative 4 feet, 0. When you put the absolute value on there, it then takes stepping forward 4 feet, moving back the absolute value of negative 4 feet,
Oh wait.
which adds a fault.
What about if you like diagonal?
It doesn't matter.
Oh.
Most of when we're going to use this mostly when we're traveling on a straight line. You travel all over the place, it gets a little crazy, but you can do that if your velocity function is something crazy like t squared plus 17t minus 4. Okay. Just a little note to file away. This is probably flashcard worthy. Okay, so now we're going to talk about the mean value theorem. The mean value theorem is also known as the Meltdown Theorem. You'll see why in my explanation. I don't know how many, if you go to Cincinnati next month for the National Calculator Convention, which happens to have a seminar on calculus, if you mention the Meltdown Theorem, most people probably wouldn't know that. The technical name is the mean value theorem for integrals. We did the mean value theorem already for derivatives. What was that one? Because remember, if a function or a theorem has its own name, it's important enough to remember. Kev? Are you just going to say limits or it doesn't matter?
No, I thought it was like it goes away.
It goes away, sorry.
I was wrong. I think it was something else.
Right.
Slope of algebra equals slope of calculus.
Yeah, slope from algebra equals slope from calculus. This is something completely different. Okay, so we start with this scenario. You've got a glass full of ice. Okay, and you can all read, but I'll give you the highlights. It's a cylindrical glass, and we've got some crushed ice in there. So it's uneven and scraggly. I don't know if that's a word, but it is now. You got the scenario. Okay. It melts, what happens? Well, like it says, it gets flat and smooth. It becomes water, and the surface of the water would be flat. The question is, where is that water going to level out? So you start with a glass of crushed ice, and as the water melts, you're gonna get a certain level of water. Will it be above or below? Always?
Yes.
Okay. So now we're gonna translate that into a calculus scenario and turn it into a function. So imagine the blue vertical lines are the sides of the glass, and the ice is the red function. Okay? And what the function is irrelevant. So I've got this uneven, scraggly ice sitting inside the glass represented by the blue things. As it melts down, it will reach this level where you've got a bunch of water. In the practical world, the glass of ice is always going to be below the level that you started with because, you know, chemistry and all that other gunk that I don't care about. From a mathematical standpoint, however, what's important to realize is that the area below this line, this melting point, and the area above have to be the same. Those of you that are good, woo!
That's very visual.
This area has to equal, oh, I was supposed to change colors. This area, if you've done it correctly. Okay? In which, obviously, you're going to want to do it correctly every time. So how do we find that? There's this little thing called z, and there's this other thing called f of z. So you'll notice that z is the point, it's the x value where this melted line hits the function. So we're going to kind of go backwards here. Normally we would take z, go up to the function, come across, and we get f of z. We're actually going to go the other way. We're going to have f of z and work backwards to find out where this point is. And notice in this particular example, I've got two different points. We're just going to focus on one. Okay, so how do I find that point? By putting a dot on the board. There we go. Okay. That point where it levels off is called the average value, or f of z, or f of av. We've got a whole bunch of different notation for the same thing. I don't really know why there's so many different things to represent the same thing. Okay, so there's our melting point, or our melted level, I should say. And then z is that point where it hits the melted line. Yes?
So these aren't gonna be x-axes? Well, because aren't you finding the area above and below the line f of z instead of the x-axis?
Wait. If I answer your question, it'll spoil all the fun.
I don't know if this is like what Kim is, but like, is he saying, like, if you just find the area underneath like that part, is it the same as the average area?
All right, we'll go there. The area of this rectangle,
Yeah.
think of this as puzzle pieces. The area of this rectangle is going to be equal to the area of the stuff below that, with these two chunks filling in the gaps.
Uh-huh.
So if I could tear that off and put it in there, and tear that off and put it in there, it would make the nice pretty rectangle.
Alright, that's
So
fine.
all we're going to do is find the area of that rectangle,
Okay.
and that'll take care of the pieces above and the pieces below.
Okay.
Okay. Doing that.
What is Z defined as?
What is z defined as? The average value.
No, that's f of z. What's just the z point?
Point where it hits the x-axis.
Okay, thank you.
Okay, so notice what the left-hand side is doing. It's finding the area under the curve from each side of the glass, from A to B. That's the area of the rectangle. The other side is saying, well, how tall is that rectangle? Where is the height of the rectangle? And we're using that to find the area of the rectangle in a different way. Okay, does that make sense? This is calculus on the left-hand side. This is geometry. All right, so let me go back to the picture a second and show you what I mean by that. The left-hand side of that function, of that equation on the next slide, gives you the area under the curve from here to here. Which again is going to give us that leveling off point here by doing geometry. So the geometry says the height of that is f of z, and the width of this rectangle is b minus a. We've talked about that quite a bit, taking b minus a times f of z. What we don't know necessarily is where that f of z is, so we have to find that f of z. And you use that by using this. Now this isn't the most practical form in the world. I'm going to change it a little bit for you to make it quite a bit easier, because we're going to use it in this form. Okay, now what did I do from that yellow slide to this? I just changed f of z to f of av, the average value, because f of z doesn't spark any memory. F of av will help you remember that that's an average value. And then I just took that b minus a and moved it over to the other side.
What does it mean when you just stick it in front? Does it have anything to do with the integral then?
Just multiplies your answer by
Just
that
multiplies,
constant.
okay.
Yeah. Question?
The average value is either the area above or under that.
The average value, think of it, I find this theorem easiest to work with if I keep relating it back to that glass of ice. F of z or f of av is the level of the water when everything's melted. The function is the scraggly ice. When it melts down, it's the level of the water.
So the level of the water is the average value.
Okay.
Why is it 1 over b minus a?
Because in the previous slide, 2 previous slides, I just took that
Oh,
as in one big chunk and just divided
Oh,
both
okay.
sides by it. Okay, kind of got the idea here. So notice it's a little hard to see because the colors are off, but this purplish region, and then we've got 2 light blue regions. Those are actually colored, and then you got the pink regions above. The pink regions above have to equal the blue regions below to fill in that space so that you get a nice pretty rectangle, which is what this represents. What does that look like? Okay, so there's a function. We'll do x cubed. We've got a pile of ice in the form of x cubed going from 0 to 4. Okay, the ice thing kind of breaks down when you actually start doing it. At this point, we should be able to do that. Took the antiderivative of x cubed to get 1/4 x to the 4th, or x to the 4th over 4, however you want to write it. Evaluate it from 4 to 0, and I get 64. What?
So I know this is from when I missed on Monday, Tuesday, but what exactly is that really tall bracket thingy?
Now's not the time to ask those kind of questions.
Okay.
Yeah, you miss, you come and see me or something. Okay. Good of the many outweigh the good of the few or the one. Anybody, what movie is that from?
We're not that old.
It's an old movie. Yeah, this movie probably came out before you were born. No,
What was it?
Star Trek II,
Oh,
The
yeah.
Wrath of Khan. Yeah, probably in the 80s. Yeah. What year were you guys born?
2000.
Oh my God. I got shoes older than some of you. That physically hurt me. 2001. Oh. Anyways, okay, so here we go. We're going to do those 2 things. We're going to find the level of the water, and we're going to find out where that water would have hit the ice before the ice melted. We good? Did a little calculation up there, because we're going to end up doing that eventually. So we plug in, I did that again. Now I'm repeating, there we go. Okay. Can someone explain that to me? Where did all that stuff come from? Someone other than Cam. But
Well, like, your B is 4 and your A is 0, so basically just like plugging into the equation.
yeah. And we did this calculation. This is, the 64 is that value, so it's the integral from 0 to 4 of the function itself, and we get 16. So what does that mean? That means if you take your cubic function and you melt that cubic function down from 0 to 4, the average value is going to be at 16. Which also means that it's going to hit the function someplace. If the function were still there after you melted it down, so now we want to work backwards to figure out where that hits that. I don't know if I included a graphic here. Hold on one second. I didn't. Okay, so let me go back. Itchy trigger finger there. Okay, let me try to go back. Okay, I'm not going back. God, I hate technology. Sometimes I think if I just keep hitting the button, it'll change.
We're gonna be
Or just throw your laptop out the window.
That'll work.
Have you tried turning it off and back on?
We actually had a tech person a couple of years ago that said if it didn't work, just press the button harder.
Was he serious or joking?
It was a her, and yes, she was serious. Okay, so we've got that. So visually what's happening is we've got a cubic function. Oh, I hope this works. Oh, good. Lovely. 0 out to 4. So there are sides of the glass. Here's our function. When that function melts, it's going to melt down to have a level at 16. Okay, that's f of z, or f of AV, whatever you want to call it. Where's this point, by the way?
60 or 4.
64. 64.
Good. And my picture's not very very well represented. I should actually have this down lower, because if we did it correctly, this area should match this area. It doesn't appear that it's anywhere close, but it's good enough. Okay. So there's our f of z. Now what we want to do is work backwards to find that location, which will be z. So the question is, how do I find z?
This function equals this.
No. No. Are you just feeding her the answer? What is she, a Muppet? Yeah, do this. All right, sure, I'm game.
You said.
I hope you heard her correct. This becomes like a game of
She
telephone.
didn't tell me
You just said to raise your
anything.
hand.
You said 16 equals the x cubed.
Perfect. Yeah. We know the y value, we're looking for the x value, which we've disguised as z. So we would take 16, set it equal to z cubed or x cubed, it doesn't matter. So z would be equal to something nasty like the cubic root of 16, whatever that is. 2 point something or another. Which hopefully is what I have on my. There you go, 2.519.